Hello, my name is Joe. I'm a geology student at ASU. I just took structural geology last semester, and I'm just gonna decided to take my notes and scan them and make a video log, kind of reviewing them over the winter break. That way, next semester I'm a little bit more prepared for whatever it is I gotta do. The first couple videos will be just the basic principles of geology, like just kind of most stuff that is kind of intuitive or that you probably already know. So I'm just gonna kind of glance over that, and then the other videos would be probably stuff a little bit more in depth. So here we have the deformation of formed rocks, the force and stress equation, force over area equals stress, and geology is concerned with stress because rocks respond to force applied through an area, which basically means that like if you have just like one solid area of a rock and a point of stress, it's going to wrap around it, or if it's like a wall of stress, and it's just going to shift or move with it depending on where the stress is kind of located. The first section up here, I guess I should point with my mouse, is displacement. So displacement is basically how things move from one area. Like if both of my hands, if this hand is the start, if these are the starting point, then this hand has been displaced this distance. So that's basically displacement. And then if it gets moved over here and then put back to its original position, its displacement is 0. And rotation is just something shifting on an axis. Strain is the deformation, like what causes the deformation of rock, and dilation is the change in size, kind of like when your pupil dilates. It changes, gets smaller when it's bright, bigger when it's dark, kind of the same thing with rocks, only with different kinds of pressure. So let's move on to down here because I've got a big notebook to go through. All of these may happen at the same time. Force and temperature, pressure is equal to force in all directions. So a lot of this is just going to be me probably reading my notes and then figuring out what it is that I was trying to say or what I'm doing, so you might have to bear with me a little bit. Changes with pressure and temperature. Oh yeah, structural behavior will change the pressure and temperature, which means that, like, let's say that you have a really strong, dense rock at if it's buried and that's a little bit of heat and a little bit of pressure, not much is going to happen in that rock. But as it gets buried deeper and deeper, then it kind of becomes more ductile. It kind of moves more like a semi-solid. And as pressure and heat increase, then it becomes more and more liquid until it starts panning out to different kinds of it reacts differently. So moving on down here in this section of my notes, structural behavior, brittle break and flow. Brittle break and flow. So that's basically saying that, like, if it's too cool but there's a lot of pressure, then it's going to break, kind of like snapping a pencil. And if it's really warm and there's like a suitable amount of pressure, and then it's going to flow, kind of like silly putty or like Play-Doh, something like that. Mineral responses is nothing or unstable. The mineral composition doesn't have enough energy to be affected. That's basically just saying, like, if there's something dense or hard inside of a matrix of material, then sometimes it won't be affected, or at higher temperatures the rocks may recrystallize and could form new minerals, which means, like, it's basically like if you put, I don't know, some sugar in some water and put it on a stovetop and there's not much heat, then the sugar, a little bit of it's going to dissipate, but a lot of it's going to be there, and it takes more heat to mix all of the sugar, like disassociate all the sugar into the solution. So effects of fluids: dissolve, grow, and change in strength. Not much effects on the rock, but can form mineral-filled veins. Water can cause chemistry to be active in a rock and promote recrystallization of minerals. So this is pretty much like if there's not much effect on the rock, but it can form mineral-filled veins, which is like if there's like a space in the rock and water's pouring through that space, then the mineral can be crystallized, can kind of be crystallized in that open space, or that the water can actually cause like chemical reactions to occur within you know, like the material, like forming hydrochloric acid to, you know, dissolve limestone, something like that. So I'm not really timing myself. I'm probably going to just kind of cut these videos up later on, like in post. So I'm probably going to make them like 15 minutes, I think. So what kind of stress affects rocks? Confining stress is basically just like pushing everything together. Differential stress is like pushing things together in some areas while there's other places squish out, you know. Those little three dots mean therefore, you know, like a stress in one plane is greater or less due to geological processes. Oh, Where's my actual notebook? Oh yeah, that would help. I can actually like, because sometimes the scan isn't so good. So I'm just gonna read from my notebook too. Oh, geological, that's not a T. Well, I'm an idiot. The geological processes, therefore the stress in some directions is greater. Like, basically saying like, it's gonna do this. Like I'm pushing harder on the sides of my notebook and the top of my notebook doesn't have as much stress, so it shifts. Oh, this is my notebook, by the way. So you can see, look at the majesty. Wait, the majesty. You'll see that later. But fluid pressure. Fluids act really differently in rocks sometimes. Sometimes it can alleviate the stress in some areas and increase it in others. So fluids like water fill pore spaces and exert a force outward. This fluid pressure can cause rocks to behave as though they are at a lower pressure. And there's a lot of good videos on this online that show that when you have like something stagnant on a plane, and when you increase the plane, it's hard for it to overcome that frictional resistance. But if there's water, it basically creates a little space and it can flow down easily. How does rock strength vary with depth? Okay, the pressure increases. It basically acts ductily or brittle. So as pressure increases, this is a good diagram of what I was talking about, like how it becomes more fluid, you know, rock flows in solid state, deformation resistance, like this is the strength of the rock versus the depth, or the strength of pressure versus depth. So the pressure increases, rock may contract lightly, but when it becomes too much, the rock will either break or flow. I think that's pretty self-explanatory. Rocks become stronger with some depth due to pressure, but at great depth, rocks will more easily flow due to temperature. So the rocks, like as you confine something, like if there's a lot of spaces in between it, you're basically pushing out all that air and making the bonds between it stronger to where that it resists break. It resists the forces to break or pull it apart a lot more readily. But as you put more and more pressure and more heat, then that creates more of like makes it flow more. So let's go on to the next page then. Just gonna scroll past this guy. How do rocks respond to differential stress? So the differential stress again was the stress that comes like unequal stresses on one piece of rock. Like if it pushes together too much on the sides, but it doesn't have as much pressure on the top, something like that. So shallow is brittle. The composition rock can fracture and slip. So this is basically saying like, man, I really do need props or something. So this is saying like if there's, these are really unequal rocks. Okay, here, let's say like this is the two rocks, and you push it together. That because I'm pushing together like this, that one of them is going to shift on top of the other. Tension is basically just pulling it apart, like pulling it apart. And shear is just as something moves up and down, just kind of, you know, back and forth from the top. If rocks are hot enough, they flow. May form folds. So like where that compression stress would shift the rocks from one position to another, If they're hot enough, or if there's enough pressure, or if the rocks are weak enough, then they'll start to flow. And at depths, rock would need to have a fluid pressure to fracture from tension. So, like if it's a really far deep into the earth, that compressional stress, if there's water in that pocket, it basically lowers the compressional stress wherever that fluid pressure is, and it can cause tension and pulling apart to break, but it usually needs water to happen at depth. And shearing usually deforms rocks over a wide zone. So, like if you got a shear zone, it's usually not just one little space where it's like, oh, this was a little shear. It's usually a huge zone over a large area. So, stress on rocks. Joints. Small cracks where the rock has pulled apart by a small amount. So that's basically just a rock is jointed when it just kind of goes, it's just jointed. It's usually up and down, just kind of, I guess I'm not really describing that very well. This is like they're equally spaced and they're usually parallel to each other. So faults, a fracture where rocks have slipped past each other. So that's again just a fault, like a shear zone kind of thing. A fold is compression caused by shortening, causing layers to fold around one another. So yeah, just kind of things like just kind of weaving in and out, just folding. It's folding. Okay, so next page. What page am I on? I am on 4. I'm hoping to get like 20 pages done in one session of this because I have a lot of pages. So joints. And this is kind of a deeper look into those 3 structures I talked about earlier, the joints, faults, and folds. That's what this is probably going to be focusing on. So joints is a smooth planar fracture that cuts through rock. Joints occur perpendicular to the direction of force. So that's like if the force is pulling it out, like if something is, if I pull this book apart, right? If I'm pulling on these two, then it's gonna open right there, right? So it's basically like that, just like the book pages, like they're just kind of evenly spaced throughout a section of the rock. It happens because the tension creates a differential stress where the perpendicular stress is greater than the horizontal capacity. So basically it's just saying that the differential stress where the perpendicular stress is greater than the horizontal capacity. Sometimes I write a little bit too fast. It's basically just saying that the stress on the sides is greater than the stress pushing down. Joints usually have consistency in their spacing and can create a space for mineral veins. So, like we talked about before, water getting into different joints and creating minerals, into different spaces and creating minerals, they usually have consistency. So, like, if you're pulling apart on something, it's just you're pulling apart on the whole unit. You're not pulling apart just at this one area and then pulling apart over here at this other area and then pulling apart over here. You're pulling apart on the whole thing. So the joints are usually on one unit. They're usually evenly spaced and, throughout the entire area. Stress causes joints. The most common type of stress is from burial and tectonic forces. These put pressure and strain on rock segments, which creates joints like we see in Arizona landscapes. It's basically just talking about the different kinds of forces, and these are a special kind of joint called columnar joints, which is like columns that a lot of basalt lavas take when they cool rapidly. You can see joints created from volcanic rocks that contract as they cool. So as they cool, they're shrinking, and as they're shrinking, they're taking that extra space and just kind of creating these shapes that are usually, I think, like 120 degrees in relation to each other. The redirection of pressure can cause unloading joints. Unloading joints are when there's a lot of pressure on something, like, and then it gets lifted to the surface, then because there's not as much pressure on it, nearer to the surface, then it starts kind of breathing out, kind of expanding, and as it expands, it kind of creates joints to compensate for that material. Let's see. These are just sigmoidal forces. So sigma 1's the strongest, sigma 2 is intermediate, sigma 3 is the weakest force. So in thin layers, the joints are going to be really, really closely spaced together, and in thick layers, are going to be spaced further apart. Oh, gotta go to the next one. Okay, faults. So, description of a fault. This is the face of the fault that is below the x-axis. This is the side where water would flow down. Oh, dip. Oh, it's talking about dip and strike. Okay, so when you have a surface and it's kind of shifted like this, right? Like if a rock is sitting horizontally and then it gets shifted downwards, this angle from, it's kind of hard to, but that angle from horizontal, like this angle right here, that's its dip. And the strike is, let's say that this is going indefinitely that direction and this is going indefinitely this direction. That's the strike. So it's just the surface of the dip. So like the dip is, whatever, if you pour water on this, like it goes down this way. So then that's the measurement of the dip. Dip slip fault. So this occurs parallel to the dip where one block slides along the fault. Oh, that's basically just a normal fault. You got two rocks, it gets dipped, it gets shifted up, and then one rock slides down. The rock that slides down is if it goes down, it's a normal fault. If it goes up, it's a reverse fault, because that's if you can see right here, this is the hanging wall, and this is the foot wall, and the foot wall is the one that you would assume that if you put a ball on the fault, which is right here, this fault surface, that it would roll down. So this would be the foot wall. Oblique slip, the unit moves neither parallel to the dip or the slip. So yeah, this page is pretty good. So the dip slip fault's just it's sliding down the dip. The strike slip fault is that it's sliding along with the strike, and the oblique slip is saying that it's not sliding with the strike nor the dip, it's just kind of going at an oblique direction. And here's what I was talking about earlier, like the normal fault, the reverse faults. The hanging wall moves down relative to the foot wall, and the hanging wall moves up in relation to the foot wall, and a reverse fault. Relative displacement fault blocks. If a block is dropped down along normal fault, the drop block is called a graben, and while the higher sides are horsts. So in Arizona, we had like kind of an expansion where the crust was kind of pulled apart at different places, and what that caused is horsts and grabens, and the grabens are the downdraft blocks, and the horsts are the ones that are kind of still up higher areas. And this is where I'm going to take a break, I believe, unless I'll do folds real quick, and then I'll take a break. Okay, so folds. Look through the noise. So that's basically, this is a quote from my professor, that he was saying that when you look at a surface like an outcropping or an exposed surface of rock, that you have to kind of look through all of the other information that's there, like the if there's like bushes, if there's trees, if there's roads, if there's like just a whole bunch of like crazy other kind of formations and shapes that are inside of the rock itself. And if you're looking for folds, to just kind of pick that section out in your mind where like you see the folds. And a structure that forms when a fold is a structure that forms when beds and layers are transformed into curved, bent, and cramped shapes. So there's dome structures, which is like kind of just goes up like an anticline. A basin is kind of like a bowl, And a monocline is basically just it goes kind of up like a hill and then flattens out. Folds form from stress, heat. Some are wavy types of folds occur where heat and stress are very high, so that would be like at depth. The fold characteristics, like in a fold, you have at the top of the fold you have a hinge in the middle of the notebook, and on the sides would be the limbs. And the axial surface is basically just right there you are, is basically just a imaginary line that goes straight through that hits all of the hinges along the line. Yeah. Let's see. Axial surface can be upright. So like axial surfaces don't have to be up. It just kind of wherever the pivot point of all the hinges are, that's where the axial surface will be, and it'll just cut straight down it. And it doesn't have to go in a straight line. Like in the earth, things can fold and shift. So like the axial surface might snake with all the hinge lines. So like an overturn, like asymmetric is where the limbs dip by different amounts. So like one of them comes up like this, and the other one kind of goes out like that. So like this one's more straight up and down, and this one's more at an angle. Like an asymmetric fold. And an overturned fold is basically like a fold that just kind of went past 90 and is laying on its side. So anticline, syncline, antiform, which is like you can tell it's an anticline, it has more anticlinal kind of characteristics, and a synform, which has more synclinal kind of characteristics. And here you can see like limb, limb, hinge, hinge, limb, limb. But here's where I'm going to take a little bit of break and assess how I'm doing on the videos.